what we are going to do now in this section is we are going to try and put everything that we have learned together in trying to solve one uh, real life example. Okay. What I mean by real life example is, the data is not clean. It's not clear whether linear model is going to work or not. And just like is in real life, um, you don't often have any physics based intuition on which one is more relevant versus other. All that, right? So this data is from a bike sharing program in Washington DC. Okay. Um, any cycling enthusiasts here? Plenty, yeah. So there is a bike share program here in near the ISB road. Right? There is a stall set up, and you can go pay the rental fee. I think there is a membership. They give you a card. You swipe the card, and you can rent your cycle and use that for given period of time. Washington DC has this program. It's been running for a while. It's a large program. They kept these stalls in different places that are useful places, and lot of commuters come in. They come in the train. Parking is like ridiculously expensive in DC, so uh, they come in the take the public transport and go to the bike share program stall and swipe your card, get the cycle, go to your office, and uh, evening you again come back and return. That's the way the program is run. So what we have is data set from this bike share program. We have a hourly data set from this bike share program. The data set gives you a whole bunch of information, and your goal is to try and forecast the bike usage, bike requirement, given some set of independent variables. Okay. You need to forecast for any hour what is going to be the need, for how many bikes should be kept there. That's the problem statement. So what's the information that's given? The information is there are multiple columns. The first column that you have is the date time column, which is given as an hourly uh, the a date plus a timestamp format. Okay, and the timestamp is actually hourly, so it's at 1 o'clock, 2 o'clock, 3 o'clock. So what we really mean is that in that hour, how many bikes were rented is given. The timestamp is hourly. Season is given. That's as numbers 1, 2, 3, and 4, where 4 represents winter, 3 represents fall, 2 represents summer, and so on. Holiday, a binary variable holiday is given. When it's 1, it's holiday. When it's 0, it's not a holiday. Working day is the rest of the weekdays. Monday, Tuesday, Wednesday. That's whether it's a working day or not. Weather is given as a categorical variable. 1 represents Monday, Tuesday, Wednesday. That's whether it's a working day or not. Weather is given as a categorical variable. 1 represents clear, with clear weather, and 3 represents snow, light rain, and so on, and 4 is heavy rain and thunderstorm is happening, or a snowstorm is happening, whatever, like really bad weather. That's number 4. Temperature is given in Celsius. There is also another variable that is given, a temp. What that is it's a feels like temperature. Okay. Now, I'm sure you have felt this. The today might, I don't know exactly what the temperature today is, but what happens is the number, the Celsius scale number, tells you that it's 39-degree day. But you go out and you actually feel like your skin is going to burn, and it's like feels much hotter than 39. So some days, even though the temperature 2 days, temperature might be the same, but on one of those days might actually feel much worse than the other. this feels like temperature depends on variety of things, whether there is wind blowing or not, whether the air has humidity, moisture or not. When in Western world, when winters, sometimes the temperature might be, above freezing, right? 2 degrees centigrade, but there'll be a wind that's blowing. That makes it feel a lot more cooler than had the temperature been below freezing. Right? So the feels like temperature includes has the effect of wind speed and humidity and a whole bunch of things. So that feels like temperature is also given. Humidity is given, wind speed is given, and then information such as the nature of the guys who actually rented the bike during that given period. Okay, whether that person is a casual rider, so someone who showed up the station and showed his ID, gave his credit card number, and took the this thing because he was a tourist, or whether that guy was a registered user. Registered users are most likely, commuters who work in that area and they've gotten a membership card. They don't want to come there, show the ID, give the credit card every day. They have their membership card. They come, swipe it, take the cycle, and go. Okay. Count is the total number of rentals, which is necessarily has to be this plus that. How many people were casual? How many people were registered users? The sum of those two is going to be counted. Right? This is the information that is actually given to you. Okay. Your task is to forecast this count. Okay. How many cycles are needed in any given hour? That is what you need to be forecasting. So here is how the entire data array looks. The size of the data set is huge, but I'm just displaying the first few columns here. So these are the variables that we looked at. Date time, 1/1/2011, 00 means it's from 12 o'clock to the morning 1 o'clock, and in that time there were 16 rentals. So the middle of the night there were 16 this thing on January 1st, right? January 1st, peak winter, right? So 16 guys, crazy bike guys were there at that time. And at 1 to 2, there's even more, 40, right? And you see this pattern over here. As you start looking at, this evening times, the number of bike rentals has increased to 106, 110, and so on. Which variables are useful for prediction? All of them? Sorry? Holiday or not, potentially useful for this. So maybe I should ask, is there any variable that is not useful for prediction? Humidity? Well, humidity, I don't know. Humidity might impact, on a hot day, particularly humid day, you don't feel like going out. A temp might have that information, may not have the information. We don't know that yet. We'll have to see in the data. Okay. But by itself, it's potentially useful information. Sorry? Season versus no, see, winter you might have a different rental patterns than in summer, right? Working day, holiday again, right? It might matter because whether it's a registered user, not registered, whether it's a office goer or you're a tourist, right? The office goers, it's possible that, I mean, in Hyderabad, I don't know what the usage is, but to me, it feels like on weekdays the usage is less. Office goers don't actually use. Office goers prefer company buses or get their own car. But on weekend, they go out and rent a thing. So working day or not might matter. Any given point in time. So, okay. So there. So one suggestion is that this date and time might not be needed. But are we think about it? Do you think that's irrelevant? Depending on the time, it might be needed. So Oh, okay. No, but they will ask you at on 2017 April 26th at 3 p.m. how many bikes should I have? Wind speed also potentially useful. Casual or registered, would that be useful for prediction? You won't have that information for prediction. For predicting, what are the information that you would have? You would have temperature forecast for that day. You would have wind forecast for the day. You would have what is the time at which you need to make this thing. All of that information can be given. At that time, you won't obviously have information on how many casual riders are going to rent, how many registered riders are going to be renting. That information won't be available, right? So using these two would not make sense. Okay. Not typical non-data scientists who are given data to analyze, what they do, they put all of this data into a linear model, try to forecast. And you know what you will find? You will find perfect prediction. You know why? It will say this plus this is equal to that. That's what the model will give. And they think they've made a perfect prediction. You don't think about what is going to be available for forecast or not, right? And this is what you would do. So we need to be careful. These two values you should not use for your forecast, because those won't be available for your on the day of your prediction. Those won't be available. So we need to first eliminate these two. Now let's talk about what are the categorical variables and what are numerical variables. So season, holiday, working day, weather, they are all categorical variables. Of course, casual register we are ignoring. So those are all categorical. How about this? That is a categorical variable. Daytime. So the way the information is given to us, it's given to us as a string, right? It's a character string. It's not a numerical number, right? Let us say there are about 20,000 data points. How many categories will be there? 20,000 categories will be there. Using it as a categorical variable will mean that it will create 19,000 minus, 20,000 minus 1 independent variables and try to do regression, which is not a smart thing to do, right? So this is an information right now, it's just a label. Like in empty cars, each column had a label. The label was type name of the car. That information as such was not useful information, right? So technically you should not put this in through the regression, because if you put it in through regression, it is going to try and create 20,000 minus 1 separate variables, and it doesn't make sense. Is that clear? So let's see, with all this information that we have, let's put that into a linear model. We'll come there. 1 second. This is our first attempt, 0th attempt. Like, let's see the base model. Then, without thinking too much about it, this is the data that's given to us. The only thinking process that went in was in recognizing that I should not be using registered and casual. That is the only thinking process that went in. Okay. So I put it in all in this linear model. Okay. And it computed all of this stuff, and it's marking some of them as significant. Few of them are not significant. Okay. So, and the adjusted R squared I'm getting is 0.26. Is that high? Depends. We don't know. This is the base number I have. Now I'm going to try and play with the data and see if I can make this better. Okay. But we have some base level from which things are being made. Okay. So one of the things is, we already talked about this, the significance of these coefficients, the value of these coefficients can give you hints about if there are any problems with the data. Okay. If any of them seem unusually large, or NA as a value that shows up, it means data are collinear. Okay. Lack of significance of many of them, which you intuitively feel should be significant, is also indicative of the fact that many of the data might be collinear. Okay, so collinearity might be a problem. What do you do for, what is the first thing you need to do to solve collinearity? VIF is a diagnostic tool. You check, VIF will give you which one are the same. Step AIC will stepwise reduce the number of variables and potentially can fix your collinearity issue. Okay, but we haven't gotten there yet. We'll get there in a bit. Now, so ultimately though, you are trying to do a fit of this linear model, right? The thing with R and any of these other modern software is that whatever data you give, it will try to do your best fit. You might, and since the computation time is not much, you would, you can try and do transformations of these variables, make humidity square and humidity square times exponential of wind speed times hyperbolic tan of whatever, right? You can do all kinds of things. And the amount of time it takes to do that computation is not much. And you might end up in finding really good fits, right? But that does not necessarily mean that the final, when a new guy comes, new data point comes, it will be accurate. Because what you might end up doing is overfitting the data. Okay, which overfitting is the process where you are fitting for this specific sample, and which might not translate into a real world application where you have another sample which might not have that exact same property. Okay, because it's almost like saying, Microsoft stock got introduced in 1987. I don't remember the date, so let's say 1987 April 3rd, Microsoft stock got introduced. By now it's increased by a factor of, I don't know, 10,000. Okay, so I can give, using that data point, I can give a stock buying strategy, buy stock on April 3rd, 1987, and sell on this date. But that strategy won't work for other stocks. It just worked for that one particular sample. What I had done there was overfitting. We need to make sure that we don't do overfitting in our data. The way to avoid that is to segment the data into two separate sets, train set and test set. The idea is you split up the data, you build the model on one set, the train set, and then you do all your tuning process and all of that on that model. Then apply that model and try to forecast on the test set and see what the error values are. That is your real benchmark on how good your algorithm is performing. Okay. What these graphs tell you is that idea of overfitting. I think you guys have already been introduced to this idea of train and test, correct? No? Not in the R. Okay, so let me talk about it a little bit. The idea of overfitting is exactly what is conveyed in this graph. So I have this blue data points. Okay, I am trying to do one type of polynomial fit, which is represented by this green line. I can do another polynomial fit, which is not a third order polynomial or something. I can try to fit with the 18th order polynomial. If I do 18th order polynomial, then you can fit this data pretty darn well, because it's going to have 18 different coefficients for each one of those terms, and the resulting error you might get might actually be small. So in this case, this orange line has the mean squared error, right? The y forecasted minus y actual square of its summation divided by number of degrees of freedom. That number is actually low. For the green line, the error is actually high. The cubic fit that I did, error is high. But when I apply it to the test set, what happens is both these numbers are larger than what was there in the train set. and that is very typical. You will fit your model and you'll get one error in your train set. You apply it to your test set, the number is invariably going to be high. That's reality. That's the way life is. But when the model is overfitted, the factor by which it's high is much larger. For a model that is not overfitted, the factor by which it's high is smaller. And that is typical. This is why you need to have two separate tests, two separate sets. You tune the data on one set and you test the data on another set. Where do these two different data sets come from? Well, from the original set, original data set. So here is the example data set. I take 70% of that data and I'm going to call that as a training set. I'm going to take 30%, remaining 30%, and I'm going to call that as a test set. I tune the model on that set. Once I have the model, what I'm going to do is I am going to test the accuracy of that model on the test set and find out what the number is. If the number is satisfactory, if the factor by which it increased is not that much, then my model is probably okay. Okay. If the factor is increased by a lot, then I know that I overfitted the model. I need to try and do something else. But this is the gold standard for testing models. Okay. Separate it out into train and test set, and this is going to be a process you'll be doing all through in all of this machine learning class or text mining, whatever it is, you'll be doing this. So once you have done the training or testing, we need to measure how well is your model performing. One common metric for how the model is evaluating how the model is performing is this idea called root mean square error. Root mean square error, all it does is forecasted minus actual summation of that divided by number of degrees of freedom. Root mean square error. The root mean square error is a nice metric because it's directly interpretable. Okay, if my root mean square value for this bike fitting number algorithm turns out to be, say, 100, then what it's telling me is that the average error I'm making in my forecast is by about 100 bikes. That's the average error. Okay, so it gives you a sense. It's a easily interpretable number. So you see this in application a lot. Okay, now in this data set that we were dealing with, I am going to compute the root mean square error for our forecast. What I haven't shown you, I'll show you shortly, is that I took that data set, I divided it into train and test. I fitted the model, the simplest model that we talk about. So I fitted the model on my training set, applied the model and predict using this predict command. So the output of the train model is sent to this variable called LM bike 0. Okay, my zeroth order model. Right? I'm calling it as LM bike 0. And the way you test it is this syntax: predict using this model with the new data, which is the test data. That's the syntax. So you forecast. This will give me the forecast for the test set. I compute the root mean square error. RMSE is the command, root mean square error. To compare, how do I compare it? How do I compute it? I give the actual count from the test data and I give the forecasted count from the test data. These two arguments I send, it'll go ahead and compute the root mean square error. In this case, the root mean square turned out to be 155. What it means is that this simplest prediction that I made with my linear model makes an average error of 155 bytes for each time slice. Is the procedure clear what we are doing here? Okay. Now, actually, before we do any of this fitting, the good procedure, good set of steps to follow is first look at the structure of the data that's given to you. Okay. Understand the data that's given to you. R has this nice command called SCR, which gives the structure of the data. I'm reading this bike share file and I'm giving the structure of this thing. So it gives me a data frame, and the date time column has about 10,886 entries. Okay, different date time stamps, right? This is why we chose to ignore that particular number. Season has these entries and so on and so forth. It's giving me all of them. Okay, but the thing is, season is given as numbers 1, 2, 3, 4, right? Are they numbers or are they categories? They are categories. Holiday, category. Working day, category. Weather, also category. All of these are category. So the way I specify something is a category is in R is using a command called factor. Okay, when I say it's factor, I send the day is actually I can send working day is a factor. I set the weather is a factor. I explicit when I say that, the linear model knows that it's not an analog variable, it's a factor variable. It needs to be split into n minus 1 dummy variables before you do the linear regression. That's the code you're sending when you say it's a factor. Okay, but many of you guys said that, you know what, I should not be ignoring this date time column, right? So what I'm doing is I'm trying to use that date time column. I'm converting that into date and I'm computing the weekday, whether it is Monday, Tuesday, Wednesday, or Thursday, because Monday might have a different rental pattern than Wednesday. We don't know. We need to see, right? We look. So I take this date time and I convert that into a weekday. From that, I extract the day and then I convert it to weekday and I send it to this variable called day. Okay, and I'm also declaring that day is a factor. Okay, so this is what I have done. I can also do one more. From this string, it's got date and the hour. I can go ahead and extract from that string the hour number. And that's what I've done. I've extracted the hour number from there and I'm sending it to time. Is this an analog variable or is that a categorical variable? It's a categorical variable. Even though time as such is an analog number, we are dealing it with as a categorical variable. We are trying to decide whether 1 o'clock that represents that midnight category, and 4 o'clock is the evening bike rental category. So we are marking these as categorical variables. So the questions do not always have the same answer. I think after the very first day of lecture, when I introduced what was analog variable, what was categorical variable, if I asked you what is time, you would have said that's an analog variable. True, that was the right answer. But it depends on the context. In this data set, that's a categorical variable. It's not an analog variable that we are dealing with. Now, so when the data set is given, you need to look and analyze the structure of the data set. But you should also plot and try to understand patterns in the data that is there. So let's try to do that. Let's see what patterns exist in the data. So what's being plotted here is the hour number, okay, versus different seasons. Okay, 4 seasons are there. I'm plotting this data over there. What you see, all of the seasons seems to have some pattern where there is a peak in the demand that happens around 8 o'clock. And then it drops. Then there is another peak around 5 o'clock. Why is that? Office time. So it being weekday might be actually important. We did create a value whether it is weekday or not, but it looks like, looking at analyzing it by this time, we realize that whether it's a weekday or not, it might actually be important. We'll see whether that turns out or not. What also shows is the season is important, right? Obviously, the fall is where the highest rentals are. Winter is where the lowest rentals are. So good. So we know that these are all important variables. Let us check whether the type of the weather is important or not. We separated out the weather into 4 categorical variables too. And let's look at that. And again, people mostly rent when it's good weather. And there is one instance where in very bad weather, someone rented. So that's a not really doesn't really happen too much on that. But this is again it fits in with our intuition, right? This is again very important. You look at the data, analyze the structure and data, make sure that everything makes sense. Okay? That's an important step. Here is a split over weekdays. Okay, weekday was not a variable that was given. We took the date time and we converted that and it created a weekday variable, right? This process of taking the existing variable, trying to do some manipulation and creating new variables is called as feature engineering. Okay? You might increase the number of variables than what is actually given, depending on whether you think it's important or not. This is again a very important process in doing analysis in data science. Okay, feature engineering, most of the time when a real data comes, it's not the only data that you'll be working with. You'll try to see if that data contains more information than what is actually revealing to you right away. Okay. In this case, we extracted the day count. What can you say about this? The weekend pattern is very different than the weekday pattern, right? Weekday by 7 o'clock and 8 o'clock, the demand is very high. What happens over the weekend is that people are waking up late. Of course, not this bunch. You guys probably wake up at 6 o'clock, 7 o'clock to come to over here. But what happens is the rental starts to pick up only at 11 or 12. Okay. So that's again a potentially useful information, right? So I'm glad that we separated out the weekday information from the this thing. So let us so the hour of the day matters. I'm glad we extracted that information from the data set. And when we add that predictors, the hour of the day and the date, whether it's a Monday, Tuesday, Wednesday, we added that information, we get a higher R square. We started with 25% around that. Now I have around 63%. Okay. Same amount of data was there. It's just that we decided to now use that information, which was not directly available, but extract information that might be potentially useful. Putting that there increased our this thing. Do you guys remember what was the root mean square error there? Root mean square was 155 bytes was what the error was. Now when we do that, the value is 110. Okay. So substantially decreased, right? Good and close to 30% improvement. Okay, so definitely are we getting a better forecast. What do we need to do after doing the linear model? Step AIC to find out whether all variables are relevant or not is something that we need to do. We also need to check residuals. Residual plots need to be checked to see whether they are still relevant or not. What does the residuals tell you? This is the way real data is going to look like. Good. So there is one thing that we can tell, everything is complicated. One thing we can talk about is this, it's not normal distribution. Okay. Now there is so many variables. I have no idea what I'm going to start transforming with. Right. But in addition, this pattern, there's this weird pattern there. Right. I mean, this of course there's no pattern. It's a good thing that data is just like splashed everywhere. But somehow there seems to be this nice line that this data is creating. And we need to understand why that pattern is and see if there's something we can do to the data that might potentially make things better. Okay, so this is our initial analysis. Let's go on to R, and I'd love to hear your suggestions on how we can improve this. One second, let me just load this data while by share. Okay, sorry. Can one of you help me with installing that packages with R metric and this? Someone had a question. Meanwhile, I'll answer the question. Thank you. Yeah. 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 Correct. Correct. Excellent. So, um, the the point that this thing is both of them installed. Cars also there. Car was also there. No. So, did you understand the question? The question was, it looks like the pattern seems to be different on weekdays versus weekend. Okay. So he's asking, should we not put them in a, but we are putting a separate categorical variable, right, to capture that. Correct. So what do you propose we do? Excellent suggestion. So that I have never I haven't had that suggestion till now in the other batches. So right away we have some potential for improvement. Let's we will check that. Brilliant. Any other suggestion that is um, that is obviously that we are missing out or anything? We should perhaps, the patterns are actually, the rental numbers are actually very different whether you're thinking about night time or whether you're thinking about afternoon time and all that, right? So perhaps if we create aggregated categories and make it into maybe three or four segments in the day, right? Late night segment, early morning segment, office hour segment, midday segment, returning office hour segment, make it a separate segment and provide that into this thing. Maybe that can increase the predictability on that. Okay. Again, we are using the existing data and manipulating the existing data, trying to create new features from that existing data. It's called feature engineering, right? So what I'll do is let me load this uh, up, like share. That was the thing. I'm going to start by first declaring all of these as factors. Okay, and now I'm going to divide this into training set and test set. This is something we talked about. So what I do is this train set and test set are divided. Not just the first 70% is going to be trained and the next 30% is going to be test. That's the bad way to do it, because maybe recent times the trends have changed, right? So what we do is we randomly pick a 30% from everywhere as a test set. Okay, this is done by this command called create data partition. Okay, create data partition, and in this case I'm actually dividing it to 75%. That actual number doesn't really matter. I mean, people do 70%, 75%. That's about the range typically it's done. Now, using this original data of bike, I'm dividing that into train and test. That's what I'm doing here. And here was my first, the simple model, which gave me R squared is 27%. Simple one. And error for that model turned out to be 155. When you play with this data set, you might actually get slightly different numbers, because since the test and train is being picked randomly, you might get different numbers for your test number. So the numbers might be slightly different, but this is the order of magnitude you should get. And what I've done here is I'm creating the weekday column. sorry, weekday column, and I'm extracting time and putting all of that information in. This was the improved number that we got after creating time as a one more category and adding weekday as a category. That's the improved one I got. Predicting for that one, a new error turned out to be 110. So this is where we have discussed till now. Now what I'm trying to do here is I'm adding part of the day. I'm going to segment the day into different time periods. Time period of late night segment, early morning segment, midday segment, and so on. So I'm going to say our number is less than 22 to our number greater than 7. I'm going to call it as set 1. Then our number less than 10 to 3, I'm going to call it as a different one. So each category, I'm going to divide it into multiple categories. Each day, I'm creating into multiple parts. Oops, sorry, I didn't mean to do step by step. But okay. What happened was, let me just run this model. Once I created the part, and let me look at the summary of the model. This is the model summary. The model summary has estimate of slope and day path, which is what we created, 4-day path. What is it giving us? What does it mean? It means it was correlated information. The information that was there in that day part was contained in some other set of variables. So even though we thought that might be a useful one, turns out that in this case it is not a useful one. So we do that, and it's only few of them are significant. The times are very significant. Time of the day you can see is very significant. Day part was not significant. So what we do step AIC, which will remove unnecessary variables. It's doing all of that, and let's see what set of variables it thought was important. These are the ones it thought was important. The season, weather, temperature, feels like temperature, humidity, wind speed, day, and time. These are all important after step AIC. Okay. I'm making the forecast and computing the new error. The error is still 110. I did step AIC. Before I did step AIC, it was 110. Root mean square error was 110. After I did step AIC, I've removed unnecessary variables. My error is still about the same. The error is not going to, error performance is not going to improve after you do step AIC. Step AIC doesn't improve the error performance. It just removes unnecessary variables. It's possible that when you remove unnecessary variables, the error might slightly increase. But in this case, it didn't really increase. That's fine. We reduced the variable and we still got the values that we wanted. Now, here is what I'm going to do. I'm going to run the summary output of all of this, the forecasted value from my, for the counter. This one, from my test data, I'm looking at, did the summary of the data. When I do summary of the data, it gives me the median, mean, third quartile, maximum number of bikes rented, first quartile, all of this information is given. Okay. My forecasted data is this, and I did the summary of that. What is showing up here? Anything obvious? Mean is about the same. Third quartile is there. Maximum is lot small. Minimum is minus. My forecasted value, the lowest forecasted value is minus 165. Does it even make sense? We are doing bike count, right? Count of the number of bikes. It's giving me negative numbers. Is it reasonable for it to give negative numbers? It's a linear model. Linear model, lines exist all the way from plus infinity to minus infinity. The straight line is possible that it can give values negative, is reasonable for a linear model, but it doesn't make any physical sense. So what do you do in this case? Thing is, your client does not care what modifications you do to the data. All he cares about, you need to give me good prediction, right? Right now I'm giving negative number as prediction. Doesn't make sense. So what you are going to do is, after the linear model predicts something, you just set a if else statement. You say that if the number is negative, reduce it to 1 byte. Okay, minimum 1 byte. Reduce it to minimum 1 byte. So that's what the statement is. So I'm saying we don't want negative numbers. So I'm saying the modified output is, whenever the output from test 2 is less than or equal to 0, I'm going to set it to 1 byte. Okay. Once I do that, let me check the root mean square error. The root mean square is now lower because there were previously negative numbers being given. Now I'm giving 1. So obviously the error is going to be little lower. That's the now there is another metric that is often used. I don't know whether I've mentioned it in the presentation itself or not. No, I guess I haven't. Called root mean square log error. Very similar to root mean square error, but what it does is it actually penalizes under prediction. In the case of demand forecasting example, where you are trying to forecast how many products are needed or all that, you need a metric that obviously accurate numbers. You're trying to forecast accurate numbers. That's always good, but we accept that there will be errors. But when there are errors, some type of errors are bad, some type of errors are good. When 100 bikes are needed, which is a better error for the bike rental shop? That when 100 bikes are actually going to be needed, is it better that you are saying that 80 are needed, or is it better that you are saying 120 is needed? It's better you say 120 is needed because he'll have 120 bikes. He's not going to lose any customer. He's not going to lose any revenue. No, yeah. Right. So make sure that your maximum doesn't exceed. But on a given particular day, you do not want to lose revenue. But understocking by how much is matters. So root mean square penalizes exactly the same way. Root mean square log error also will penalize you, but it penalizes you more for under prediction than over prediction. So root mean square, this was actually a test set. I'll talk about where I got the data set from, but root mean square log error, it's around 0.96. Problem with root mean square log error is there is no easy way to interpret the number. Smaller number is better, but there is no way to interpret the number. We are going to do one more modification to this our forecasting thing, and which will hopefully result in a smaller error. But we are going to look for this number, root mean square log error. We want that number to be smaller than what we have done till now, which is 0.9. Okay. There are multiple metrics people often use. Mean absolute percentage error, that's often used. Root mean square error. There's a whole bunch. In logistic regression class, I'll give you a much bigger list. Depending on the business domain, some are more useful than others. But once you understand how one is calculated, understanding how other ones are computed is not all that difficult. Okay. Now, one final, since we are almost out of time, let me just do one final modification to the model. We are trying to forecast bike numbers, which is through a linear thing, which we are getting negative numbers. Because necessarily linear values will extend both positive and negative. There is one natural transformation that will avoid this problem of getting negative numbers. That transformation is a log transformation. Okay. If the in my data, the y values, the byte count values, they are all positive, right? I can take the log of that number. When I take the log of that number, log is defined only when you have values are positive. When I take the log of that log number can be both positive or negative. That kind of data is better for a linear model to fit than a data which is only positive. Linear model, since it naturally fits both positive side and negative side, it's better to transform your variable that needs to be fit in a way so that it has both negative and positive values. So log data turns out to be a natural transformation to try in this case. So what I'm going to do here is this. I'm going to, instead of fitting count, I'm going to fit with log of count. Okay, same numbers that are there, but only thing I'm doing is I'm fitting with log of count. I run the linear model there. Adjusted R squared turns out to be slightly better, not dramatic, but the real test is we are going to do step AIC and find out root mean square log error, what the value is. Okay, I'm doing step AIC and I'm trying to do the final number of root mean square log error. Step AIC is running. Final value of root mean square log error is 0.62. Now, before I compute this, I need to remember this. When I make a prediction, I fit it with log values. So the output of the prediction is also in log values. I need to take exponential of that to convert it into non-log values. So this number is a log value. I took exponential of that, converted to the non-log number, and then I computed the error in the forecast. That number is a small number, 0.62. The modification that you suggested, I haven't done, but after the class, maybe we can quickly do it and see what the number turns out to be. This is the benchmark to these. This is what other classes have been able to come up with, 0.62 root mean square log error. There's still one thing that we haven't done till now, which is for this modified thing, we haven't looked at the residual plot. Let me look at the residual plot. I already said in this residual plot, instead of plotting all four, I'm choosing to plot only the first plot. It showed this weird, bizarre pattern, right? Now that I have taken log and done the same thing, it will show a different pattern. But it still shows this bizarre lines now. Previously, it showed this one curve over there. Now it's showing these bizarre lines. This kind of pattern should raise warning bells. You shouldn't get that kind of pattern. And I don't know exactly what this pattern is. Let us see if we can find out what those data points specifically are. The way you find out is through this command called identify. This command identify tries to identify what those points are. So what I do is I can just go with my mouse and click on those lines. It will give me the index of that point. Okay, I'm clicking on a bunch of these points, and this is going to give me the index of those points, and I hit escape to this thing, and I'm going to look at all of those points and see what is causing this bizarre pattern. So those points, these are the points that form this line. It's giving me the index of that, 791, 691, whatever. I'm plotting and looking at this index. Is there anything common among those points? Season is all 1. Holiday is 1. Yeah. So they're all y value for all of them is 1. When y value is 1, the value that you are forecasting, right? Are you forecasting an integer or are you forecasting an analog number? You want an integer for answer. But linear regression, y equal to mx plus c will give you continuous numbers. You are forecasting continuous numbers. But you are comparing the error with an integer, right? So if you forecast 1.2, your error will be 0.2. If you forecast 1.3, your error will be 1.3, 0.3. So the error values, what's happening is this line is because you are forecasting analog number but comparing with digital number. Those are all the points which represent that error that you have made. It's not a pattern that you should be worried because of nonlinear pattern, but this kind of line comes in whenever you are trying to forecast discrete value through linear regression. Linear regression forecasts only analog numbers, so the errors will have that discretization error, and that discretization error is what is often seen as line. So this line corresponds to data points that are 1, this line corresponds to data points 2, data point 3, and so on. So that's something to remember when you're trying to using linear regression or any of these models to forecast a quantity that is actually discrete. Then this kind of residuals are to be expected. Okay, so let me stop the class with that. What I would encourage you to do is use this data set in leisure. Now there's going to be a different set of exercises that are planned for your lab class. Okay, you will have hands-on experience working with this data, but at home definitely try to use this data, this bike share data, and see if you can do some other transformations. Maybe log of humidity might be useful, maybe square of some variable might be useful, or as you suggested, trying to split the data into working day and weekend might be useful. See if you can improve the final root mean square log error. Okay, this data set was part of a competition that was done at Kaggle. So there is this website called Kaggle. I don't know how many of you know about that. They keep running these competitions. I would strongly encourage you guys to register at the site, and when these competitions come, try downloading the data and play with the data. Usually the data is real world data and give you invaluable experience on how to handle real data, not this clean textbook data, right? Real data, that's the experience you need. And you can submit your results and they will give you rankings where you stand compared to other people who are competing. And Kaggle is a well-known site now that you can actually quote your rankings in your resume when you try to apply for a job. That for this particular competition, my ranking was that. As data scientists, our experience, our skill set improve as you handle more and more of this real data, because you need to use different mix of techniques in order to make forecasts. So please do try to do that. When you go to Kaggle's website, you will see this data set and you will see what is the current leader's accomplishment. But the current leader's accomplishments is going to be using neural networks or something. But you will also be able to find out what is the best accomplished number using linear model, and you have an option of trying to beat that model. Okay, so please do try that. Have a good week. I'll come back when we meet on next Saturday or Sunday. I forget. Sunday maybe. Yeah, we will talk about logistic regression. Okay.